Swayam Prabha. Digital India. Educated India.
Good morning. So, today we are going to start our first introduction to induction motor. So, if you look at it, I have given you some introduction to synchronous generator already, and actually all these devices that I am going to talk about, synchronous generator I have talked about, induction motor I have talked about. So, this is their traditional name, but basically a synchronous machine is a more appropriate word, because a synchronous machine can be used both as a generator or as a motor. It is basically not like a diode, it's not like, it's in some sense bidirectional device. You push in mechanical input, you will get electrical output. You push in electrical input, you can get mechanical output. So, what I am trying to say is, when we have a mechanical input which we, through electromagnetic induction, rate of change of flux and all those principles, we convert it to electrical output. Of course, observing the law of conservation of energy and all that, then this is usually called as a generator action. So, this is called a generator. And when you have a electrical input and you get mechanical output, you get a motor action. Now, there are three types of machines usually that we talk of. One is a synchronous machine, and again you have synchronous generator and synchronous motor, of which I would say that this is a more traditional use. And then you have, then you have induction machine, of which you can have induction motor and induction generator. Now, of this is the more traditional use, but now wind generators, especially in the wind farms, they may be actually induction generators. So, induction generators is also getting popularity. Then after that you have DC machines. And again with DC machines also, you can have a DC generator and a DC motor. There is many varieties here. They both are popular, both are, of course, AC machines are more popular than DC machines because our supply is AC. So, it is easy to directly interface a AC machine rather than a DC machine. But among DC applications you can see both DC generator, DC motor, because wherever you need a DC supply probably you also need a DC generator. Of course, you can use a rectifier and convert AC to DC and then directly feed a DC motor. So, that is also there. Here there are 2 or 3 types: series motor or generator, shunt motor or generator, then compound motor or generator, and separately excited motor or generator. In induction machine construction point of view, you have squirrel cage. The squirrel cage name comes basically like the rotor looks like a cage in which you can probably hold a squirrel, but it does not mean anything more than that. And so, you have a squirrel cage or a slip ring construction. And in synchronous generator, we have already seen that you have 2 pole machine, which is usually called as a alternator, and this is usually used with thermal or gas turbines, which create high speed value. Or then you will have multiple like 8 to 10 poles or 4 poles, or some poles always are number of even poles. These are usually low speed machine which is used for hydro, etc. So, here in a sense you are talking of high speed and low speed. Now, whenever we talk of machines, especially when we talk in terms of motor action, I am going to talk of motor action now. So, whenever we talk of motor action, then we will always think about torque speed characteristic of the machine. This is something that we are very interested in. So, for example, since we have some introduction to synchronous machine already, and suppose you are trying to use this synchronous generator is, let us say, the first quadrant is the generator action, let us say, or let us say first quadrant is a motor action. So, this is the motor action. Then when the speed will synchronous machine will always operate at one speed only, and that is the synchronous speed. Actual rotation will be in the mechanical radians per second. So, if it is a 2 pole machine and a 50 hertz supply, then it is running all the time at 3000 rpm. But if it is a 4 pole machine, then it is all the time running at 1500 rpm, and if it is a 6 pole machine, then it would be running at 3000 by 3, that is 1000 rpm, and so on. But whatever is that rpm, you do not have so much control on that. So, you can only control torque, but really not the speed. So, in that sense you can see that, I mean, for example, if you want to use it as a traction machine, AC traction machine or something like that, directly it cannot be used unless you have a variable frequency supply. Because like for example, if you want to run an electric car, or if you want to run a railway engine or something like that, and if you fix supply frequency and then if the speed gets fixed, then you need to actually ramp up the speed in a traction work, electric traction work, or a EV or something like that, and you need to have it running over a various number of speeds. So, in electric traction traditionally now things are changing, I mean, but because the power electronics is playing a major role in how we can modify the torque speed characteristics of the machine. But traditionally the DC machines were far more popular. They allowed us to have a torque speed characteristic which looked like something like this, that when the speed is low you can have a torque very high, and as the speed increases the torque reduces. So, it comes some kind of an inverse relationship. So, this is where you would be like coasting at high speed, straight you are going, but when the when the carriage is picking up, the train is picking up the speed, at that time a high torque is required. And one thing which is there, very interesting thing with electrical motors is that this is very vernier or smooth, the torque speed characteristic. This is very smooth. So, unlike IC engines where you have these gears and you have to change the gears and then adjust this thing, of course, power input has to be still adjusted, but that smoothness is not there that in other engines. But with electrical motors or engines which run on electricity, the DC, the AC, both of them, the induction or the synchro or the DC machine, you get very smooth torque speed characteristics. So, you sit sometime in an electric vehicle and then sit in a combustion engine vehicle, and you can feel the difference. You will also feel that the noise levels are much lower here. There is nothing burning here honestly, because there is a battery somewhere and has charged it in an electric vehicle, but there is nothing burning here, no emission of gases, and all that combustion and the piston moving inside the cylinder creates a lot of noise. You then need a separate silencer to damp out that noise as well as emissions and then bring it out and so on. But if you see an electric vehicle, oh God, so smooth it is, so noise free it is, it just it will just go away and you won't even notice it, and you can really ramp up the speed from 0 to say 100 kmph in 60 seconds or something like that. Fantastic torque speed characteristics that you can get with them. So, though I am going to teach to you the induction motor in a very traditional way, the way normally it is used, like for example, it is used in refrigerators or air conditioners or things like that. But what I am trying to sort of say is, in fact, the post EV, the field of application of these, they were always there in electric traction, trams, all the railway trains that you see on in India, you know, you would have that wire running at the top, and that will bring the electricity. So, or for example, you know, just take diesel generator, I mean, I think diesel locomotive, I mean to say, not diesel generator. So, what you have got there is actually a, first of all, like you have a diesel motor, a normal IC engine diesel motor, but like you have seen with your cars and this thing, you need so many gears to get a proper speed control and all that. So, you will not have that great value directly. If you use a DC motor and try to drive a big locomotive, you will not be able to do much of a speed control. You do not have there like first gear, second gear, third gear, fourth gear and smoothness of the speed control and all that. So, what you do is you use this diesel motor and then use this to say drive a DC generator, or it could be AC generator and induction motor, but I am just writing right now a very traditional way of doing things, which is drive a DC generator. The DC generator will give you electricity output as DC. Now, that you connect to the DC motor, and then the driver gets his controls here. That of course, the driver also needs to, these controls have to also in some sense control the flow of how much combustion you are going to do, because the stored energy is here basically, which is in the form of fuel. In a EV, instead of this, this will be replaced by a battery, and then you will have a DC or right now I will not mention which machine, but you will have a electric motor. This battery, a electric motor, and then your driver gets a control here. And here you need to refill the diesel when the it runs out, or in a, even in a IC engine or not. Here you need to charge the battery when the charge run out. But look at it, in both the places finally it is the control is coming out of electric motor. This is because of the vernier or very smooth torque speed characteristic that you get with the electric motor. Now of course, this is these EVs are therefore also much more simplified. So if you look at it, there is lot of empty space really available for you. One of the major components is a battery, then the space taking component is a battery, then there is a motor, and there is nothing really major, anything more than that. But in a IC engine requires much more intricate thing, and quite a bit combustion engine, silencer, gear drives, this, that, so many things are get involved there. So I think I have at least at the bare minimum sold to you the excitement of having studying, excitement of at least studying the electricity motors. And with power electronics coming into place now, there are just too many nice things to study. Today we will be studying, we will start our study with that of a induction motor, and the device that I am going to talk about is known as a 3-phase induction motor. So you already know that we have a 3-phase supply. So therefore, normally a big workhorse of the industry is a 3-phase induction motor. So you can imagine that this, let me shorten it a bit. Yeah. So let us say that this is my stator, and let us say that I have a distributed winding. Now you are very comfortable, I hope, with the distributed winding. So this is the R phase, this is the Y phase, and then they are of equal span. I mean, slight my drawing is bit defective, but this is the B phase. So I have this RYB winding, 3-phase winding installed here, and now I will draw a rotor. So this is a rotor. So I have a stator and a rotor, and the stator is connected to 3-phase supply. The stator winding could be either delta or star, is delta connected or star connected. It is usually grounded. If it is connected as a star, you would also ground it for safety and controlling the unbalance purposes. Now rotor, for the time being, okay, let me just tell you what is a cage rotor construction. So what I have here in a cage rotor construction is Actually it is a spherical thing, but I have drawn it slightly like that, but it is actually a spherical thing. And then I have bars. So, these are copper bars, and this is also copper. So, in a sense what you can think of is that these copper bars, now you should think of sort of uh, like if this is the top view, then this is, if this is the if this is the top view, then seen from above you would only see this bars, you know, coming here. This is all that you are going to this is all that you are going to see when you see, if this is, if this is the top view, then the top view of this will be just these bars which are there and which have been short circuited. Now, why do you short circuit is, I will come to that point a bit later on. You could instead of that also have this, absolutely this way is also done. This way is also done, that instead of having these bars here, you could be having R phase winding somewhere here, then will come the Y phase winding somewhere here, and then you would have the B phase winding here, and these windings. So, A phase winding will come with one slip, let us say like this, and another terminal of it will come. So, a winding has to have two terminals. So, this will come on one ring, this will come on another ring, and these are called as slip rings, because to connect it to anything in the stationary thing on the outside world, let us say you want to connect a resistor here which is placed in one particular location, then these brushes will connect to the slip ring. This would be carbon brushes or so, and this could be copper, for example, ring. The moment there is this touch and one thing is fixed and another thing is rotating, this will create wear and tear, but by having a adjustable resistance, we get some control on what we want to do. So, variable resistance gives you control, or you could just set this to 0, which is short circuited, in which case what you would end up is having a 3 phase winding on rotor which is short circuited. And if you have short circuited these windings which are on the rotor, then as well you can just distribute bars across the periphery, then as well you could just distribute the bars uniformly across the periphery and just short them, and that is how you get much simpler construction, which is cage rotor construction. It has a lesser degree of freedom because I cannot control from here, I can also control input dissipation by adjusting the resistance, or I can give controlled input from outside world. I can give controlled input from the outside world. So, I get more degrees of freedom to play with the torque speed characteristic when I go for a slip ring kind of a construction with this thing. But first we will just discuss the induction motor, which is a cage rotor construction. So, you can think of it as if you have a three phase winding. Sometimes I will say that I am having 3-phase winding, proper distributed, so on, just like that on the stator, but which is short circuited for the sake of discussing the physics of the problem, but which is effectively translated into a very simple assembly of a cage rotor, squirrel cage rotor construction, which is as follows. So, now you have some idea of and this is of course what is here, this is all iron, is it not. So, this is all iron core, at inside of it is, this is iron core, this armature is, this is also iron core, and this is your air gap, and the flux lines can go like this, come back like this, go like this and come back like this. So, otherwise it is a very similar kind of a construction that we have seen in the with a synchronous machine. The generator stator side construction is more or less identical. Rotor, there you had a DC magnet, so either you had salient pole or a turbo alternator kind of a construction. Here the rotor construction is similar to what we saw in a 2-pole turbo rotor construction, except for the fact that it is a simply distributed cage rotor which is short circuited, which can also be effectively imagined as a 3-phase winding similar to what we have on the stator, but which is short circuited. Now, the point is to tell you upfront, this machine, if I connect to a 3-phase supply and no load or unloaded on the rotor, what is going to happen? What is going to happen is that in an ideal world is usually in electrical engineering free of resistances, free of friction at the mechanical thing and so on. So, in such an ideal world, the induction machine will start rotating at synchronous speed. Which is for 3000 RPM. But if I make in the DC, if I make effectively a 4-pole kind of a construction on the rotor or on the stator, then I can cut down this synchronous speed to 1500 or 750 if I go for a 8-pole construction and so on and so forth kind of thing. So, again the distinction between mechanical radians per second and electrical radians per second remains. You can simulate multiple number of poles again here, but again that story we have to defer to this to a future for a future discussion. So, now the question that should come into your mind is, let us say for the time being that we are talking of a 2-pole construction, and I said that it will start rotating at the synchronous speed. How? When the when imagine imagine that, okay, let me put like this. Imagine that I have let us say a magnet, okay. Let us say I have a magnet here, this is the say this is my north pole, this is my south pole, and slightly the construction is not very good. I mean, I am not have something like this, a magnet which I am rotating, okay. This is rotating like this. So, the field is I am sorry. So, let me call this as the north pole and this as the south pole, and so the field lines are, let us say, going somewhere like this and coming back. And suppose I rotate this magnet at a very high speed, and let us say there is a, I have installed, it is not such a means on this geometry, let us say I have just a small iron piece which is there. Then what will happen? It is like, let us say, like this is the iron piece, and I have a magnet north south. Somehow I have managed to build a, like, think of a horseshoe magnet or something like that, you know, and that horseshoe magnet I am rotating at a synchronous speed. That is what I am trying to sort of show here, that horseshoe magnet is rotating at a synchronous speed, and inside of that I have kept a iron piece like this. Then intuitively, from your experience, intuition, you would know that if that horseshoe magnet is rotating at certain speed, say 3000 rpm, immediately this iron piece will try to start rotating at the, and catch up with that horseshoe magnet. So as to keep the reluctance of the net thing to the minimum. We have not actually studied the physics of it, but we can see this happening, that iron let us say it is like a nail, let us say this is like a long nail. That long nail is not just going to stay there, it will always try to catch up with that rotating magnet, and therefore it will start rotating. And now suppose you have connected some load to that, then it will try to rotate that load. The moment the load is rotated, load means there is some torque which is opposing, then mechanical work will get done, and that mechanical work has to be supplied for rotating that horseshoe magnet, which in our case is coming as a electrical input. We will see to that. Right now in this horseshoe magnet, since I am rotating it, it looks like I am putting mechanical energy here and getting mechanical energy output here. So, it is coming like a mechanical to mechanical transformation, but in a motor actually it is going to be the electrical in the motor it is going to be the electrical output, which is input, which will come to rotate that something similar to horseshoe magnet, and then the work will get done on this thing. In between there will be some losses, there will be electrical losses, there would be some mechanical losses, that part we will discuss much later on. So, the thing is, first thing that I want to bring to your attention is that this 3-phase winding, all right, Now comes the most important concept of the which is that of how to simulate the rotating magnet from a stator winding, and the stator winding is my 3-phase stator winding. How do I simulate a rotating magnet? Once I have done that, then I can say that the rotor is going to simulate that iron piece which is going to try to catch up and rotate with respect to the magnet. So, there are two steps that we are going to do. First, we want to show that 3-phase AC supply connected to 3-phase distributed winding on the stator, also sometimes called as armature, will create so a rotating MMF, a 3-phase stator winding. This is the key concept, a 3-phase stator winding carrying mounted on stator in our case, carrying 3-phase distributed winding. This is also we have talked enough about the distributed winding. So, this winding is distributed in space carrying 3-phase balanced currents will result in a rotating magnetomotive force MMF wave. It is also called as a rotating MMF wave. Since there is a MMF, so automatically you divide it by the reluctance, and you will therefore also get a B wave, rotating flux density wave, which is effectively saying that I am having a rotating magnet at the stator. Without causing anybody to do any rotation there, I am actually from electricity itself creating by this method, I am going to create a rotating MMF wave. How? First I will do it mathematically, because mathematically it is much more straightforward to show. So, let us say that this A phase winding here, or the R phase winding, or the A phase winding which I have set up here, okay. This is this you remember, this will create we had discussed this earlier, that you will get a MMF wave if it is carrying a current I, it will give you a stepped, sorry, this figure is not coming out very good, 1, 2, 3. Then again it will step down and so on. So, it will create basically, which if I connect a smooth curve and talk of the fundamental component and all that kind of stuff, then this will create basically if it is carrying DC current of say 1 ampere or 5 ampere or whatever, then if suppose it is carrying a current of I, then the MMF or the B or the MMF which is going to be distributed is going to be Ni cos of theta. So, if I have a phase winding, it carries a current IA, then with respect to the theta equal to 0, which I have set it with respect to the A phase. Now, these axes are fixed. Once I have fixed this, now the B phase winding and the C phase winding, for that I cannot change this theta equal to 0. Now, it becomes fixed like this. Then the B phase winding, so the MMF of A phase winding is Nia cos of theta. Now, similarly I have A, B and C phase. So, the axis of this is 120 degrees away from the axis of this. So, therefore, because the axis itself is 120 degree and then whatever B phase current, suppose B phase is also just a simple DC current exactly identical, then it will get a waveform like this 120 degrees away. So, therefore, the MMF of B phase winding is going to be NIB cos of theta minus 2 pi by 3, that is 120 degree radian. Now, if both of them are carrying the same DC current, which they will not be, because actually I will connect A phase to A phase supply, B phase to B phase supply and C phase to C phase supply. But if they were, for example, just carrying same current, then this would be the waveform for the A phase, then this would be the waveform for the B phase, and then similarly you would get a distributed waveform for the C phase. But they are not actually, they will not carry the same current. A phase will be connected to A phase supply, B phase will be connected to B phase supply, and the MMF of C phase winding will carry a C phase supply, which is cos of, either I can write it as theta minus 4 pi by 3 radians, that is minus 240 degrees, or I can write it as theta plus 120 degrees, or in other words theta plus 2 pi by 3 radians. So, I am following this convention. Now, at any point theta, now this theta is of course, this is my theta equal to 0 line, and I am going theta degrees here, and on this is how I am moving on the circle, which is shown here as movement opened up and shown like this, and at any angle theta. So, therefore, if I ask you question, what is the MMF at an angle theta? So, somewhere here, this from here to here is theta, and I am asking you what is the MMF that is created at this angle theta, then what you would say? You would say that it should be superposition of all the three above. This is of course assuming that iron is not saturated, it is like a linear element, air gap is of course as a linear element, and anyway means this is fine, MMF will be anyway superposed. Based upon linearity, later on I would say that the B is proportional to MMF, because and that is how I will come to that. We will come to that. MMF, therefore, the net MMF, F net basically, F is usually abbreviation used for MMF, MMF, the last F is picked up and written as F of theta is going to be equal to NIA cos of theta plus NIB cos of theta minus 2 pi by 3 plus NIC cos of theta plus 2 pi by 3. But now remember IA, let us say IA is Im cos of omega t, means that I have chosen appropriately the reference like that. So, that t equal to 0 corresponds to the peak current of the cosine wave for the IA of t. Then, and if they are carrying balanced currents, then this should be minus of 2 pi by 3 and IC of t should be Im cos of omega t minus of 4 pi by 3. So, in that sense, because the currents are a function of time, F net will not be just a function of theta. So, the correct way to write this would be F net of theta comma t, because if the windings were carrying constant current independent of time, then F would only be a F net would only be a function of theta. But because my currents in the windings are a function of time, the MMF is going to be distributed a function which depends upon where in space I am looking. Suppose I am looking in space here, what is the MMF? Then this MMF is not one fixed number based upon its location in space, but it also depends upon the time. It will keep on changing with, probably keep on changing with respect to time, because these currents are my function of time. So therefore, if I just substitute this and this here, here and here, then I will get F net of theta comma t will be equal to NIM cos of omega t cos of theta plus NIM cos of omega t minus 2 pi by 3 cos of theta minus of 2 pi by 3 plus NIM, the C phase current is cos of omega t minus of 4 pi by 3, and the C phase winding is also sinusoidally distributed in space, but its axis is with respect to A phase winding axis lagging by 240 degrees. So, therefore, cos of theta minus 2 pi by 3. So, I can take the NIM common and write this as cos of omega t cos of theta plus cos of omega t minus 2 pi by 3 cos of theta minus of 2 pi by 3 plus of cos of omega t minus of 4 pi by 3 cos of theta minus 4 pi by 3. Okay. I slightly prefer to write it like this, it is one and the same because the products commute. Theta my eyes are used to it, that is all, nothing, this way of writing, there is one and the same because the products are commuting, but our mind has memories, you know, and this is what I have written. Okay. Now, the question is what is this, and I will first give you the answer, then I will derive the answer. This is nothing but 3 by 2 NIM cos of theta minus omega t. When you solve that complicated thing there, you will get this as 3 by 2 NIM cos of omega t. Now, what does that mean? First understand this. This means there is a rotating MMF wave. Why do I call it as a wave? Because if there was an observer in the air gap, okay, observer in air gap rotating at a speed omega. So, it is sitting at some place in the air gap and it is also rotating at the speed omega. Then what will happen is this d theta by dt that you are getting for him is equal to omega. So, whatever his initial position be, say theta naught or something like that, then he will just see a constant whatever theta naught, he will just see this constant MMF or B, and he will just see that value because he is also rotating at a synchronous field with respect to air gap. But on the other hand, suppose I just fix theta, that means the observer is fixed, let us say theta equal to 0 degrees, just to keep my life simple, it could be 30 degrees, 5 degrees, 10 degrees, whatever. Then what will happen? He will see he will just see a sinusoidally varying field in B in time, because his location is fixed and this is a rotating magnet. So, it reaches its peak, reduces, reverses, comes back again comes back to its peak value, and this variation is sinusoidal in time. So, he will just see a alternating B, alternating MMF, alternating flux in time if it is fixed. If the observer is rotating, let us say in air gap at speed omega m, then he or she will see a rotating MMF wave or a magnet, if you just want to physically think of it as a magnet, at a relative speed of omega s minus omega m. Omega s is the synchronous speed at which actually with respect to the ground or the stationary thing, the field is rotating at omega s, but my observer who is probably sitting on the rotor and the rotor is probably rotating at speed omega m, is then rotating at a speed of omega m only. So, then he sees that the field is ahead, that rotating MMF wave is ahead of him and is rotating at a speed of omega s by omega m. So, this omega s by omega m for future use divided by omega s is usually called as the slip in per unit. So, this is called as a slip in per unit, or in other words omega m can be written as omega s into 1 minus s. So, if it is 10% slip or 0.1 slip, then the speed of rotation is 0.9 times omega s. So, if 3000 rpm machine into 0.9 if you do, then it will become 2700 and so on. So, this is again this slip term will come for usage later on, let us not worry about it. So, the point is that a 3-phase distributed, symmetrically distributed, properly distributed 3-phase winding in space carrying balanced 3-phase currents in time creates a rotating magnet or a rotating MMF wave, and this is like, this is my B distribution and this this is with respect to my theta in the space, this is how the B distribution is there, but this is itself, this wave itself is rotating at a speed of omega. So, how does it simplify? Now, the question really is, how does this calculation simplify to such a simple beautiful thing? So, what I am going to do is use the fact that 2 cos A cos B is equal to cos of A plus B plus cos of A minus B. So, suppose for example, you set A to 0, B to 0, this becomes cos 1, this becomes cos 1. So, 1 plus 1 2 and this is 2 into 1 into 1, this is 2. If I set this to 45 degrees and 45 degrees, then it is 1 by root 2 into 2. So, this left hand side is 1. Now, if I set it to 45 degrees, cos of 90 will be cos of 90 degrees will be 0 and 45 minus 45 will be 0. So, therefore, cos of 0 will be 1. So, 2 into 1 by root 2 into 1 by root 2 is equal to 0 plus 1, which is 1 is equal to 1. I do not have to do this, what I usually check once whatever formula that I write, I just put 1 or 2 points in it to make sure that whatever I have written is correct. Otherwise, sometimes confusion can happen. I recommend this to everyone, to cross check. and not be fully on your memory. Anyway, ठीक है. So, cos of theta, so therefore, what I am saying is cos of theta, cos of omega t, 2 cos of this is going to be cos of theta plus omega t plus of cos of theta minus of omega t. Now, take the next term, 2 cos of theta minus 2 pi by 3 cos of omega t minus of 2 pi by 3 is going to be equal to cos of a plus b, which is theta plus omega t minus 4 pi by 3 plus of cos of a minus of b. So, the minus 2 by 3 and minus 2 pi by 3 will cancel out, and I will get cos of theta minus omega t, because this and this will cancel out. And then 2 cos of theta plus of 2 pi by 3 cos of omega t plus of 2 pi by 3 will give me cos of a plus b will be theta plus omega t minus 4 pi by plus of 4 pi by 3 sorry plus of 4 pi by 3 plus cos of again just a theta minus of omega of t. Now, when I add these three together, this will just, these are all identical terms. So, I will get 3 cos of theta minus omega t, 3 cos this thing plus cos of theta plus omega t plus cos of theta plus of omega t minus 4 pi by 3 can be written as minus 4 pi by 3 itself plus cos of theta plus omega t plus of 4 pi by 3 can be written equivalently as minus of 2 pi by 3, because if you have what I am trying to sort of say is cos of psi is same as cos of psi minus 2 pi. So, if I subtract minus 2 pi from here, then I will get minus 2 pi by 3 coming here. So, or 4 pi by 3 go back from here is same as going 240 degrees going back like this is same as advancing here by 120 degree, whichever way you want to look at it. So, now the thing is, what is this sum? The thing is, what is this sum? And it turns out that this sum is 0. So, let us call this as theta plus omega t as psi, then this will be cos of psi plus cos of psi minus 2 pi by 3, that is the third term, and cos of psi minus of 4 pi by 3, that is the second term, and this will sum to 0. You can expand it and check, but I will give you one simple thing. You write first term as this first term is the real part of e to the power of j psi. Then the second term is going to be the real part of e to the power j pi minus 2 pi by 3, and the third term is going to be the real part of e to the power j psi minus 4 pi by 3. So, basically you are looking at real part of e to the power j psi plus e to the power j psi minus 2 pi by 3 plus e to the power j psi minus 4 pi by 3. In other words, you are looking at real part of e to the power j psi can be taken as common 1 plus e to the power minus j 2 pi by 3 plus e to the power minus j 4 pi by 3, and but this is usually, this can be shown to be, have we done it earlier? 0. Anyway, does not matter. Think of this r as e to the power minus j 2 pi by 3, whether I have done it earlier or not, it is not does not matter. Then this expression is 1 plus r square, and this is a geometric series. So, it is 1 minus r cube upon 1 minus r having 3 terms, and so if I substitute for this this is 1 minus e to the power minus j 2 pi by 1 minus r, but e to the power j 2 pi or minus j 2 pi is 1. So, therefore, this is 1 minus 1 by 1 minus r. So, it is 0. So, therefore, this thing sums to 0. Since this thing sums to 0, this thing comes to 0, my my MMF F net will sum out to, since you see I have taken a everywhere actually I am having here cos theta cos omega t. So, it is half of this, then this is also I am having cos of this into this. So, this is also half of this value, this is 2 times, this is 2 times. So, when I have expanded it, I have expanded this whole thing together. When I have expanded the whole of this thing together, basically what I have got is this is as good as saying that I multiply these things by 2 and divide this thing by 2, and then when I expanded and summed it, it came to 3 cos of omega cos of theta minus omega t, because the other terms summed out to 0. So, therefore, the net MMF wave has finally just turned out to be 3 n by 2 n I m cos of omega t by 2. So, I have done this by 2, then 2, then used all this stuff, but all this stuff basically just simplified to 3 cos of theta minus of omega t, because everything else went down to 0, and hence the net MMF wave just summed off to 3 by 2 n I m cos of theta minus omega t, and this is a rotating MMF in the air gap, this is a rotating MMF wave in the air gap. We will stop here for today, continue in the next class. Thank you.